Alright, the ideal gas law, which I abbreviate as IGL. Why is this worthwhile to learn? Well, when I start thinking about the ideal gas law, I start thinking about my mountain bike and design of shock absorbers. And so, if we think of a shock absorber, it's kind of a cylinder here. And there's a piston that moves up and down. We can just kind of draw it like that. And we can model a gas inside this cylinder here with the ideal gas law. Oh, and this cylinder looks a lot like what goes on in a car engine. And we can model the fuel and air mixture in a car engine with the ideal gas law. And we can model the flow of the air through the exhaust system with the ideal gas law. And I start thinking about airplanes. And when we're designing airplanes, we need to predict the density of the gas at elevation, and I start thinking, I can model out with the ideal gas law. So, in summary, the ideal gas law is useful for the design of many, many things. So, how do we use the ideal gas law? You might recall from earlier classes that the ideal gas law is given by a simple equation. And let's write this here. PV is equal to nRT. So P is the pressure of the gas, V is the volume of the gas, N is the amount of gas in number of moles, R is the universal gas constant, and T is the temperature. And so we just simply plug numbers into this equation. And the number of moles here is a way to describe the quantity of gas. And there's another way to do this. So if we're talking about the amount of gas, one way to talk about the amount of gas is the number of moles. Another way to talk about it is the mass of the gas. And these two ideas are related, because we can use a capital M, and this is called the molar mass, and the molar mass is the ratio of the mass of the gas to the number of moles. So we can write this as an equation, which is lowercase m over n, and very often as engineers, we don't want to work with the number of moles, we want to work with the mass of the gas. And so we can take this equation and stuff it right in there. And let's write the universal gas constant a little bit different. And so if we do that, let's go ahead and go through the steps. So we have PV is equal to nRT, and so N here will equal the mass of the gas divided by the molar mass times R and T. And this R here is the universal gas constant. And we make this a new symbol, which we also use R, and this is the specific gas constant. So specific gas constant. And so let's rewrite the equation. PV is equal to the mass of the gas, the specific gas constant, times the temperature. Excellent. Now, if we want to work with moles, we can use PV is equal to N, universal gas constant times temperature. If we want to work with mass, PV is equal to M times the specific gas constant times temperature. So we have two useful equations. And it turns out there's another useful equation. And what we do here is we just simply recognize that the mass of the gas divided by its volume, MOV, is the density of the gas. And when we do that, we can rewrite this equation. And it looks like this. P is equal to rho RT. So this is the third useful form of the ideal gas law. This is the second, and we have the first one written up above. And so the key idea, we have three possible ways to write it. They're all equivalent. We can start with one of the equations and derive the other two. And so how do we use the ideal gas law? We look at our problem. If we want to work with density, we grab this equation. If we want to work with mass, we grab this. If we want to work with moles, we grab equation number 1. It's that simple.